Uh, Hello everyone. In this video, we are going to study open mapping theorem. This open mapping theorem is the one of the important theorem in functional analysis. The statement to open mapping theorem is the following. So let me scroll down to here. So the open mapping theorem is so suppose we have x and y are Banach spaces, and then we have T is a map bounded linear operator from x to y, and also it is surjective. Then the map T is open mapping. Moreover, if T is bijective, then you can find the inverse operator, T inverse. And actually, this T inverse is actually bounded and continuous by previous because it is open mapping. So this is our goal to prove in this video. Okay, in order to prove this theorem, we need one lemma that I'm going to prove first. So the first lemma we want to prove is the following. Suppose we have x and y. These are Banach spaces. Again, T is a bounded linear operator and surjective from x to y. And then I look at the open ball of radius 1 centered at 0. Then the image of this guy contains a open ball around about 0. So this is the most important part in order to prove open mapping theorem. Okay, the proof of this lemma has 3 steps. The first step, what we want to prove is this. Okay, the image of B or 1/2. This is a open ball of centered at 0, radius 1/2, and the closure T of this guy closure contains an open ball. And then second step 2 is what, and then you take image of BO 1/2 to the n closure. So this one also has open ball around 0. Okay, this is what we want to prove. And then finally, we can find the delta, so that BO delta is contained in T B01 closure. So this is we have 3 steps. Okay, before we go further, I will give one convenient definition. Suppose A is a subset of X, and the alpha is a scalar. So K is a scalar. This is a field. This is a field, and I have omega is in X. Okay, then you multiply scalar. You multiply A set by scalar. That says that you just multiply alpha to the element A. Okay, alpha A. For all A is in A. And then this A plus W omega is the just translation. So A plus W equals the set of all A plus W when A belongs to large A. So this is just the translation. So this is translation. This one is more like what? Dilation, or if alpha is less than, modulus alpha is less than 1, this is called dilation or stretching. So, okay, extend and dilation. Okay, so let's try to prove step 1. Okay, so I'm going to prove this one. So the step 1 is so here is step 1. So this is step 1. We want to prove step 1. Okay, first of all, so we have to, okay, here is one of the important property. X and Y, these are Banach spaces. Then you have a complete space, like a complete. Then we have one of important theorem, Bayes category theorem. So we have to apply Bayes category theorem. So in order to apply Bayes category theorem, then we need some work. So if you take any element in X, then 2 times norm of X is finite. Then you can find the integer the greater than this number. So and then you choose K is integer, so that 2 norm of X less than K. So that implies X norm is less than K over 2. Okay, then implies what? So this implies X belongs to B 0 K over 2, right? And then you can take K outside. Then X belongs to K times B or 1/2. Okay. So you take any element in X, then there exists K such that X belongs to this. That implies what? Okay, that implies X is actually union of K, B, 0, 1/2, K from 1 to infinity. So I think it's better to put K0. So I'll put K0, K0, K0. So the reason why I put K0 is like this K0 is one of K appears in here. Okay, so this is just that one. Okay, then and then T is surjective. We know that assume that T is surjective. Then surjective means Y equals Tx, and then X is the sum of this number, this set. You just put over here, and then the property of union, then that becomes union K from 1 to infinity, T K times B 0 1/2. Okay. And then T is linear, so you can actually, this one came in here because T is linear. T is linear, and this becomes a union, K from 1 to infinity, K times T, B 0 1/2. Okay. Of course, this guy is less than closure, right? Closure. And then this everything are subset of Y. So this is Y. So therefore, I can also write down Y as K from 1 to infinity, K times T 0 or 1. Okay. So here, this is one. And then we know that Y is complete. Then we apply Bayes category theorem. Then there exists the K0 is natural number such that the interior of this one, because this is already closed, the interior of this one is non-empty. So this is the most important theorem, Bayes category theorem. So this guy is interior is non-empty set. By the way, you know, one interior set is always open. This is always open. Okay, interior is open set, and this is non-empty. Then you can choose Y0 star is in open in Y, right? This is open in Y, so there exists Y0 star in Y, and then you have epsilon ball, so that this one belongs to here. So actually, I can write down interior of this one, and then interior is always less than original set. So it's better to like this one. Closure. Okay. Then make it clear. Okay. Then what I'm going to do is this one. Then you multiply both sides 1 over K0. So then 1 over K0 B Y0 star epsilon star, this belongs to T B 1 0 1 half closure. Okay, and then okay, look at this one. So then this set is, you put it in here. So then if I should explain this way. Oops. Okay. So if y belongs to 1 over k0 y0 star y0 star epsilon star, then oh, let me see. It's hard. Okay, then you put it in here. So this guy, you see, this guy is the same 1 over k0, and the set of y such that y minus y0 star is less than epsilon star. I think it's better to write it in this way. And then you put it in k0, that is exactly y over k0. And then you this guy, you multiply k0 both sides, it's still okay. Then epsilon star divided by k0. Okay, then you can replace y divided by k0 by this one. Then you have y minus this norm, not absolute value, norm y tilde minus y0 star divided by k0, norm is less than epsilon star k0. So this is the same set. Okay, so that implies this one is b. So I put y0 star divided by k0 is y0. So this is y0. And then I put epsilon to be epsilon star divided by k0. So y0 epsilon. So this is what I have. So if I put y0 equals y0 star divided by k0, epsilon equals epsilon star divided by k0, then b star, I put b star equals b y0 epsilon. This guy epsilon is actually the same as this one. Then this belongs to t b0 1 half closure. Okay, then you translate. This one is the open ball of open ball around about y0. So then you translate by minus y0, then b0 epsilon equals the b0 epsilon minus y0. Then you take y0 both sides. So this is what we have. So finally, up to here, we proved step 1, right? Step 1 was BT, B0, 1 half closure has open ball. So this is what we finished the step 1. So this guy has open ball. So we have finished step 1. Now we try to prove step 2. The step 2 was this one. And then you put instead of 1 half, I put 1 over 2 to the n. So this guy contains open ball about 0. So that's what we want to prove. Okay. So and then we just continue what we did so far. Then what I just explained, that B0 epsilon, this belongs to this guy. Okay. So in order to prove, I want to prove this guy belongs to, this whole thing belongs to T, B, O1 closure. So this is what we want to prove. So we want to prove this guy equals B, 0 epsilon. This one belongs to here. in order to prove, I want to prove this guy, I just mentioned. Okay. This is our goal. Let me use this guy. Okay. So this is what you want to prove. So let's take any element to y belongs to. This guy is very confusing. Okay. So take any element y belongs to t b0 1/2 closure minus y0. And then y plus y0 belongs to this set. Okay, then we know that y0 is already in t b 0 1/2 because of here. So the b star b. So this from here y0 already in t by 0 1/2 closure. Then you can take sequence wn zn in b 0 1/2 such that un, I put t zn converges to y plus y0 because y plus y0 belongs to this set, and also y0 belongs to this set. Then you can take wn converges t wn converges to y0. And then from this one, you consider gn minus wn. That, well, you see, zn. So you have a 0, radius 1/2. This is radius 1/2 ball. You have wn is here, zn is here, and the distance between these two less than 1. So then gm minus m belongs to b01. Okay, b01, and then t gm minus n from here converging to y. So that implies y belongs to where? So y belongs to t b01 closure. So that's exactly from previous line. That's what we are done. So we take any element y in this set, y belongs to here. So that what we prove, this guy belongs to this guy belongs to t b01 closure. Okay. Then finally we proved b0 epsilon is subset of this guy from here. So from here we have this. So step 2 is gone. Then we can prove further step 2. So then look at here, b0 epsilon over 2 to the n. And then you take 1 over 2 to the n outside. Then it equals 1 over 2 to the n, b0 epsilon, what he have. And then what we just proved in the previous line, then b0 epsilon is less subset of this guy. And then this guy belongs to here. And then t is linear. Then you put 1 over 2 to n inside. So that's what we have. So finally, what we have, b0 epsilon over 2 to the n belongs to this set. So this is what we proved in step 2. So step 2 is finished. Okay. And then finally, we want to prove step 3. Step 3 is one. So B01 closure contains open set. That we have to use the result in step 1 and step 2. So our goal is this B0, B01 contains open ball about 0. That's what we want to prove. Okay, then we just continue from previous one. So we have what we want to prove is B0 1/2 epsilon belongs to this set. So in previous step we know that when n equals 1, then this one belongs to T or B 0 1/2. Okay, then our goal to prove this is it. So we want to prove this one. Okay, this one. Then I take any element y is in this set, and then by definition of a closure, I can choose y1 is in T b0 1/2 such that the norm between y and y1 is less than epsilon over 2 squared. Okay. And also y1 is in this set, then you can choose x1 is in this set such that y minus tx1 is less than epsilon over 2 squared. And then here, this guy is this one, then beings y minus tx1 belongs to b 0 epsilon over 2 squared. And then in the step 2, we prove this guy. Using step 2, then this guy is less than here. Okay, belongs to this set. Then this one belongs to this set. Then there exists x2 such that y minus t x1 minus tx2 is less than epsilon over 2 to the cubed. Okay, and then again this one belongs to this set, and this one again step 2 belongs to this set. Then I can choose x3 is in here, so that this one is less than epsilon over 2 to the 4. So we repeat this process, okay? Then we obtain a sequence xn belongs to b 0, 1 over 2 to the n, such that so the norm of this guy is less than epsilon over 2 to the n plus 1. Okay, then you see, now you look at this part, this one, so you have a linear, then I put Zn to be k from 1 to n, xn. Then you can prove this Zn is Cauchy sequence. So you take for any n is greater than m, I compute the norm of Zn and Zm. Okay, difference between two elements, Zm minus Zm. Then by definition, so this guy is less, the first, this one, so I assume that n is greater than m or equals to m. The remaining part is this part. So we have only this part. And then when take m goes to infinity, then this one less than 2 to the m plus 1. So you see this one, 1 minus r, so 1/2. And the first term is 2 to the m plus 1 over 1. So I have 1 over 2 to the m. So this implies Zn is Cauchy sequence in X. Then again, we know the X is complete. Then this Zn converges to some element. Okay. Now T is bounded function. Bounded linear is continuous. Then Tzn also converges to Tx. And then I compute, then finally we have y minus Tzn is less than epsilon over 2 to the n plus 1. So from here, star, here, then it plus Tzn converges to y. Okay, and then here Tzn converges to x, Tx, and this guy converges to y. The uniqueness of limit y should do the same as Tx. So y equal Tx. And then furthermore, we can also prove x norm is less than 1. So to prove this, and then I compute norm of summa is k from 2 to the n, xk. This one, triangular inequality, you have this. And each norm is less than 1/2. no, each norm is less than 2 to the n. So this guy is less than one half. Okay. And then I take okay, then I have zn minus x1 norm equals zn norm minus x1. Then this guy is previous, this is one half. This guy is what is this the same, these are the same, but this is one half. So finally gn norm is less than x norm plus one half. And then we know that x norm is less than one half. Okay, so I have not equal here. That's why I proved it in this way. So finally we have x norm is less than 1. So that x belongs to B01. Okay? So what we proved here, y equals tx, and then x is element in B01. So y belongs to T B01. So finally, we take any element in y is in this. Y, you take any element in y, and this y belongs to this set. So finally, we proved this one. So that implies T B01 contains open ball. Okay, so we have very long lemma. Okay, so the proof of this lemma is very long. Okay, so now we are in a position to prove our open mapping theorem. So see, so we want to prove T is open map. So let's take any open subset A is in X. Our claim to prove TA is open set. In order to prove open set, you take any element Y in TA. I need to find the open neighborhood of open ball around Y. So we need some this. So you have to find some open neighborhood around Y. Okay, this is what we want to prove. Okay, so since T is surjective, Y is in TA, then you can find X in A such that Y equals TX. And we know that A is open set. There exists R such that BXR belongs to A. And then you translate BXY by X. Then that's exactly that B0R is also open ball around 0 because this is already open ball. And then by look at you take 1 over R outside. This is exactly B01. Okay? And the previous lemma, we proved this guy is T B01. So this one contains open ball or about 0. So by previous lemma, there exists delta such that B0 delta belongs to this because this is actually T B01. Okay. Then from here, and you multiply both sides by R, B0 R delta equals this guy, and then this one belongs to here. You multiply both sides R, and the T is linear. This R came inside the T, so you have this guy, and this will be cancelled here, and then T0R is again BXR minus X. Okay, and then again T is linear. Again T is linear. This is T BXR minus TX. Okay, then we have here this guy and this guy. And then you add TX both sides. Then translate by TX plus B0 R delta belongs to this set. This is again subset of TA. So finally, this one is the same as Tx R delta. So this is Y R delta. So finally, we have B Y R delta belongs to TA. So that implies TA is open set. Okay, so that implies T is open map. Finally, we proved T is a open map. Open mapping. And then now T, suppose that T is bijective, then T inverse exists. So, and then we know that we proved T is open map, that is exactly T inverse continuous map. Okay, T inverse continuous map. So, and T inverse is also linear, so T inverse is bounded. So, it's continuous and bounded are the same when for the linear operator. So that we have proved the open mapping theorem. So, okay, so this is the end of this video. So I will see you in class.